Hello everyone, welcome to another lecture of robotics. I hope that all of you are fine. In the previous lecture, we studied about configuration space and the difference between configuration space and workspace. We also studied about how to calculate the degrees of freedom of a mechanism or a robotic arm. In this lecture, we shall study about configuration space topology and its representation. For more details, you can read the chapter number 2 and section 2.3 in the book Modern Robotics. So from section 2.3 till the end of this chapter, you can find related material to this lecture. And now we shall see what is a configuration space topology. Topology means shape of the configuration space. So here we shall see for different types of mechanisms and different kinds of configurations. What is the shape of the configuration space? So point on a plane, it can be represented by two coordinates x and y, and the topology of this kind of configuration is also it looks like a plane also. So if you want to find the topology, so this is a plane and it's also two-dimensional. And the point on sphere, let's say a ball or something like balloon, so this point can also be represented by latitude and longitude, as we have seen previously, and this surface of sphere will also be a two-dimensional. So we have seen that a point on a two-dimensional plane, okay, it looks like something like this, a 2D plane, a point x, y, and then a point on a sphere that looks like a ball. No, sorry, not xy. Here we have latitude and longitude. So this is latitude and also longitude. So yeah, they both have two-dimensional configuration spaces, but they look different. Both plane and sphere are 2D, but their shapes are different. So you see that this has some kind of rectangular shape, the configuration space, but this one is also two-dimensional, the sphere, but the shape of the configuration space or its topology is different. Two spaces are topologically equivalent if one can be continuously deformed into other without cutting or pasting. So it means that you can convert a sphere into an oval shape, okay, with some deformation, but you cannot convert a sphere into a plane or a plane into a sphere without cutting and pasting. So these two shapes, these two topologies, they are not equivalent. Okay, so what are the examples of topologically equivalent configuration spaces, you can say? For example, you can say that a sphere and an oval shape, they are topologically equivalent. So here you will find these two things equivalent. So with a minor deformation, you can change a sphere into oval shape without cutting or pasting, but this thing you cannot convert into a plane or vice versa. So this is not possible here. A sphere and plane are not topologically equivalent. So if you have to convert a sphere into a plane, then you need to do cutting. You have to cut it and then make it straight, and then you can do it. But since the cutting is involved, so it means these two topologies or shapes, they are not equivalent. Okay, the circle is written mathematically as, so now we shall see that how we can mathematically represent the topologies. Okay, so we write down mathematically a circle as S, or we can also write it S1. So S is for sphere, and S1 means it's a one-dimensional sphere. Okay, similarly, a line is written mathematically as, you can write it as E or E power 1, indicating a one-dimensional Euclidean space. Okay, so a sphere can be can be written mathematically as okay, so for the line we can also write it as since a point in E is usually represented by a real number, in the Euclidean space we use real numbers. Okay, after choosing an origin and a length scale, it is often written as R or R1 instead. So we can also write here like R, or we can also write R power 1. So this is real numbers. So if you want to represent a line mathematically, you can write either e power 1 or r power 1. So this is a standard. For a sphere can be written as power 2, which means that it's a two-dimensional surface in a 3D space. This is how you write down sphere. A n-dimensional space is written as write it as r power n, which is an Euclidean space. Okay, topology of a space is a fundamental property of the space. So shape of the space is a fundamental property and is independent of how we choose coordinates to represent points in the space. So the shape of the space, whether it's a plane or a sphere, so the shape of your configurations, the shape of your configuration space, this is its fundamental property. Okay, and it has nothing to do with the coordinates, how you represent it. For example, here you represent x, y. Here you can represent latitude and longitude. So the coordinates that you choose to represent your configuration space, it has nothing to do with the shape of the configuration space itself. So these two things are independent of each other. You can also use here also the xy coordinates for the sphere also, and we shall see later how. See spaces as Cartesian product. The C space of a rigid body in a plane can be written as r power 2 into s1. Since the configuration can be represented as a concatenation of the coordinates xy representing r square and the angle theta representing s1, s power 1. So a rigid body in a plane, you remember that it can be represented by coordinates x, y, and theta. So this r square maps to your xy, and your s power 1 maps to your theta. So this is how we can also represent it, your C space as a Cartesian product. So this is your plane and this is the one-dimensional sphere or the circle. The Cspace of the PR robot can be written as, so what is a PR robot here? PR robot means a robot or a mechanism having one prismatic joint and one revolute joint. How we can represent its, or how we can write its Cspace? So we can use r power 1 cross s1, because there is one prismatic joint which shows a linear motion, let's say along x-axis, and then there is one revolute joint which shows angular motion, let's say along with theta angle, with angle. So this is how we can represent as a Cartesian product. The Cspace over 2R robot can be written as, so what is a 2R robot? A 2R robot is a robot having two revolute joints. So this can be written as S1 cross S1. So one circle and then another circle we have. So we cannot write it as s power 2, because s power 2 means a sphere, but here s1 cross s1 is equal to t power 2. So t is a torus. The torus looks like something like t is equal to torus, and it looks like donut. Like this shape. So this is how we represent the Cspace of a 2R robot. To perform computations, previously in the previous slide we have seen that how we represent the, what are the shapes of different types of the Cartesian, the configuration spaces, and let's try to draw some of them and see visually how they look like, how the topology of our Cspaces looks like. So a point on a plane So number 1, point on a plane. So a point on a plane, it means it's a 2D, two-dimensional plane. And how it looks like, the topology of your configuration space having these coordinates. It can be represented by x, y coordinates, your configuration space. because it's a point, so there will be no orientation. Theta doesn't exist, only xy. And so your configuration space will look like something like a triangle plane, and we have already seen that mathematically we can represent a point in a plane by for a point we have discussed about how we represent a circle and a line and a sphere, and a point we have here. We have said that a Cspace of a rigid body in a plane can be written as r power 2 cross product with s power 1. So a point has no dimension, so it means that it will have no orientation. That means this portion will not be present. Only this portion will be present. This is the mathematical representation of a two-dimensional space. Okay, so we can use it here. Mathematically, it can be written as Euclidean power 2 or r power 2. This 2D space, x and y. Okay, what else we can have? Then a spherical pendulum, how we can represent it? A spherical pendulum, it looks like a pendulum that has a surface area of like a sphere, and it can move around, and this can be represented by two angles, longitude and latitude. So its configuration space is two angles, and this can be, its topology will look like a sphere. And you know that mathematically how we represent a sphere, we have already seen that here. A sphere can be written as s power 2. So we can write it as s power 2. So the configuration space will look like a sphere, a ball. Okay, number 3, we have 2r robot arm. So robot arm having two links. And this is the first link, and this is the second link we have. So theta 1 and theta 2. Okay, how it's what will be the shape of its configuration or the Cspace? We have already seen that it can be represented by s power 1 cross s power 1, which is equal to t power 2, not s power 2. S power 2 is a sphere. T power 2 is a torus, which looks like something like a donut. So yeah, so its configuration space will look like a donut. Something like this. So yeah, so this will be your theta1, here will be your theta1, and here will be, this one will be your theta2, this angle. So this is how your configuration space will look like. If you want more examples of your configuration space, then you should look at the table 2.2. Refer to table 2.2 in the book Modern Robotics. Okay, so yeah, so this is the shape of the configuration space, and now let's see how we can represent our configuration space. To perform computations, a numerical representation of a space with real numbers is required. So when we want to do some calculations with our robotic arm, we want to find its angle, its position, its orientation. So we need numerical representation. We have to represent our configuration space with numbers, with real numbers. Okay, so this is called configuration space representation. To represent a plane, we choose a reference frame with origin point and two orthogonal coordinate axes. So this is clear, I guess. We have done it so many times. So when we want to represent a plane, what we do here, we make a reference frame with orthogonal axes. We choose a reference frame with origin point and two orthogonal coordinate axes. Yeah. So there is an origin point here, we call it origin, and we have two axes, x and y. So that's how we represent a two-dimensional plane. This is a representation of Cspace. Okay, topology of the space is independent of the representation of the space. This is we already talked about it. Topology is the shape, and representation is the showing your Cspace with some real numbers, okay, or with coordinates. So these two things are not dependent on each other, they are independent. If a space is flat or Euclidean, then we choose coordinates to represent the space. So for a flat surface, it's easier to represent using x and y coordinates, these types of configuration spaces. And a point on this surface will have two coordinates x and y, and mathematically this can be represented as r power 2. So this will be the representation of your two-dimensional flat surface. If the surface is curved or a sphere, then we can either use explicit parameterization, which uses minimum number of coordinates such as latitude and longitude, so how can we represent a curved configuration space? So for this purpose we have already seen that a 2D surface is easier to represent, but for a 3D spherical surface which is curved like this, for that we need either explicit parameterization, which uses latitude and longitude here. And these are the longitude lines. Or you can also use latitude. So this is called explicit parameterization. We can also use implicit representation, which uses more coordinates subjected to constraints. So in explicit parameterization, we use less coordinates. For example, for a sphere, we can only use latitude and longitude, only two coordinates, to represent a position of a point on a sphere. We can also use implicit representation, where we have to use more coordinates and in addition to some constraints. We shall see how. Implicit representation of a sphere considers 2D surface embedded in a 3D Euclidean space. We use three Euclidean coordinates x, y, z subjected to constant radius constraint x power 2, y power 2, z power 2 is equal to 1. So let's see how. So this was the explicit parameterization, where we use only two of the two parameters to represent our sphere. And in implicit representation of Cspace, so what we do here, we use actually more number of coordinates to represent a sphere. So let's say this is a sphere we have, and this is a z coordinate, this is x, and this is a y coordinate. So what we do now, we use three of these coordinates along with the constraint, and the constraint is that x square plus y square plus z square is equal to 1. So this is a constraint. Okay, so we all are familiar with that. If we total have 3 degrees of freedom and one constraint, so the total degrees of freedom will be 3 minus 1 is equal to 2. So it means that a point on this sphere when will have 2 degrees of freedom. It can move anywhere in either directions on this ball or a sphere. But the representation is different. In this case, we represented the sphere using explicit parameterization, where we use only 2 of the coordinates. One was the latitude and the second was longitude, like we do it on our Earth. So this is a different type of representation of our Cspace. And the other method, using implicit representation of Cspace, we use more coordinates, like 3-dimensional coordinates, to represent a 2-dimensional sphere. Okay, so this is another type of representation. 1 constraint on 3 coordinate means 2 degrees of freedom. So yeah, so it means the sphere will have a 2 degrees of freedom. One more thing is that how we can represent, actually in mathematically, how we can represent our Cspace. So for if it's a spherical pendulum, let's say, so here we have a spherical pendulum, and we can represent it using a point on this kind of configuration space. We can represent it using if we use explicit parameterization, then we have a longitude and now we have a latitude, and so the latitude has plus 90 degree and minus 90 degree values, and here we have minus 180 degree to positive 180 degree. So so the Cspace will be from minus 90 degrees to plus 90 degree, and same is from other side also. So this will be the Cspace representation of a spherical pendulum. So we have represented it in explicit form with longitude and latitude. Okay, so let's see some advantages or disadvantages of the explicit parameterization and implicit representation. So the advantage of explicit parameterization is the minimum number of coordinates. Since we are representing the location or the position of a point on a sphere by just two angles, which are the latitude and longitude. So these types of representation of the configuration space will require less coordinates to represent the position of a point. The disadvantage of using explicit parameterization is that since the topology is different from the Euclidean space, the representation will have a poor performance at some points in space. So this is a problem with using the explicit parameterization. For example, when you let's take an example of Earth or any spherical body. Okay, it is represented by explicit parameterization, where we have some longitude and latitude lines. So we have latitude and we have also longitude here. So the problem is that, as we have seen, the disadvantage is that the shape of this kind of C-space is different from Euclidean space, which was just a rectangle. But since now it's a spherical, it will have a poor performance at some points. And what are these points? These points are, for example, here. When you go to here at this point, it will have a value of 1. Okay, so this is a problem. This is a singularity here. And one more problem is that the rate of change of longitude is different for various latitudes, rapidly changing coordinates. Another problem is the discontinuity of coordinates. So we have more problems that the rate of change of the coordinates is different. It's not like what we experience in the Euclidean configuration space. And also there are some discontinuities which are not present in the Euclidean workspaces. Let's compare it with the Euclidean. This we draw here, Euclidean configuration space. And this is the spherical C-space here. So here we have no such problems that the coordinates change smoothly in every direction. Okay, but here we have problem with the spherical configuration spaces, that here in the middle the longitude changes at a different rate, but as you move toward the pole, the longitude changes quickly because the lines, they are becoming more closer. So and this is a point, this is a, let's say, North Pole, and this is South Pole we have here. So you see that the line will be that here the lines, the longitudes have near the equator, the longitude have more spacing, But as you move toward the North Pole, this spacing becomes less and less. So this is something which we don't experience in our Euclidean Cspace or a rectangular space. This spherical, bent or curved type of spaces will have always this problem that the rate of change of the coordinates, it's not like same for all the locations. So if you are on equator on the middle of the sphere, you have to travel more distance, but as you move toward the north, you have to travel less distance. And one more problem is that rapidly changing of the coordinates. For example, you go from 0 to plus 90 degree, okay, and suddenly when you move a little bit away, then suddenly it will become a different value. So this is a discontinuity in these types of configuration spaces. You can see this is also clear from angles also. When you measure an angle, so the angle is, for example, from here you have 0, and then you have 90, 180 degree, and it becomes 360. So from 360 is directly we jump to 0 again, or you can say from 360 the angle will become 1, 2, 3, 4. So this discontinuity is not present in our Euclidean spaces. Okay, for example, here the values are increasing 1, 2, 3, 4. So after 360 there will be 361, not like 0 or 1, 2, 3 again. This kind of discontinuity in the curved configuration spaces, this is problematic. So this is one of the disadvantage. So now see, we have already seen that advantages and disadvantages of the explicit parameterization, and now we see what are the advantages and disadvantages of using implicit representation of a configuration space. So the advantage of implicit representation is that it avoids the problem of discontinuity. So if we use more coordinates and with some constraints, then we solve this problem of discontinuity or rapidly changing coordinates. But the disadvantage is that it is more complex way of representation. So if you see the implicit representation, which is here, you see that this type of representation of configuration space, it doesn't have any discontinuity because the coordinates are not the, you can say, explicit. So that's why we solve the problem of discontinuity and rapidly changing coordinates. But it has a disadvantage that it makes things more complex. You see, there are now more coordinates, we have some constraints, so the complexity is increased. We shall use implicit representation for the representation of configuration space. For our calculations, we shall use implicit representation. We shall use 9 numbers with 6 constraints to represent the 3 orientation freedoms of a rigid body in space. So yeah, whenever we want to represent the orientation of a rigid body, so we shall use a matrix with 9 numbers total, and there will be some 6 constraints. So our goal is to represent 3 orientation freedoms, 3 degree of freedoms of rotations of a rigid body, and this is called a rotation matrix. So it will be a 3 by 3 matrix in which we are representing 3 rotations along 3 different axes. And we shall study more about rotation matrices in the next lecture. Okay, now let's see one more example of a robot, and we shall see how we can represent its configuration space and its configuration topology. So let's see, we have a 2R robot arm. mean it will have 2 revolute joints. So this is the, here we have first link, and then we have here the second link here. This is, let's say we have theta1, and here we have angle with theta2, and this is link 1 and link 2. So we have already seen that we can the topology of this 2R planar robot, its topology is a torus, call it a torus, so this is actually a torus is actually like a donut. It's a 3-dimensional object, and this topology can be described as, we have s power 1 into cross product of s power 1, which is t power 2. This is its topology. And so here we have theta1. Theta1 is the angle so from here, from the center, at any point, so this angle we call theta1, and then this angle we call theta2 here. So this point can be, this point P can be anywhere on this torus, and keep in mind this torus is a 3-dimensional shape, theta2. So this is the topology of this robot with 2 revolute joints in 2 dimensions. And now we shall see what is the configuration space looks like. So as these angles, they are allowed to move from 0 to 360, and same is true for theta2, 0 to 360, or you can say 2 pi radians. So if we draw its configuration space, so we have theta2 and then we have theta 1 on other axis. So this is theta 1, and on this axis we have theta 2. So this configuration, we say that we shall draw like this. The robot can start from 0 and it can go till 360 degree theta 1, or you can say 2 pi. So the link first L1, it can move from 0 to 2 pi, and similarly the robot theta 2, it can also go from 0 to 2 pi or 360 degree. So both links or both angles can vary between 0 to 2 pi. And then we shall have some values that are within this range. For example, when theta is pi, and also the theta 2 is also pi, so you will have somewhere value here. And so if both of your angles are 360, your configuration space point will be here somewhere. So this is the configuration space of your 2R robot. So these angles theta 1 and theta 2, they can vary between 0 to 2 pi. They can have any value between these angles. So this is being shown here also in the topology, and you can see that theta 1, it can rotate 360 degree, and theta 2, it can also rotate 360 degree here, from here to here, like this, in a circular way. So it will make a three-dimensional torus. So if you want to write here the range, so how we write it? We write it down like this: 0 to 2 pi for theta 1, and also 0 to 2 pi for theta 2. This is your configuration space we have. I hope this concept is clear, and let's move to the next slide. So now we shall study about the configuration and velocity constraints. For the constraints actually limit the motion along some specific coordinate. Okay, so these constraints can be configuration constraints, or they can also be a velocity constraint that limits velocity along certain directions. So two of these constraints are worth mentioning. First is the holonomic constraints. So what are the holonomic constraints? Holonomic constraints reduce the dimension of the configuration space. For example, the distance constraints between the points of the rigid body. So if you remember the rigid body, we took the example of a coin here. We said, okay, when we select point A here, you can do it anywhere in your configuration space. You can select this point A. You have 2 degrees of freedom. But as for the rigid body, the distance between 2 points is fixed, constant. So this will be a constraint dB is constant, so this will be a constraint, and namely a holonomic constraint, because when you want to select the point B select the point B, you have already a constraint, which is a distance between these 2 points, which is constant. So you're not able to select this point outside the radius of this circle, or even the inside. You have to select this point on the radius of this circle, this dotted circle, because of this distance constraint. So normally this point B should have also 2 degrees of freedom along x and y, but since it has a constraint, which is a distance constraint dAB, so its degrees of freedom, or you can say the configuration space, has been reduced. Now it has only 1 degree of freedom, which is the rotational one, and its configuration can be described by the angle theta, the theta angle of this circle, okay, where the point is located. So these types of constraints that reduce the dimension of your configuration space, they are called the holonomic constraints. So yeah, and then we have another types of constraints, and these are called non-holonomic constraints, and they reduce the dimension of the feasible velocities. So now take an example again of a coin rolling on a table or on a plane. So we call it, let's say we have a plane here, and this coin, it has this angle theta, and then we have one more angle, which is a phi, this angle shows the orientation of this coin in your on the plane. This angle is, we call it phi. So, and then this point, the point that is touching on the table, we can represent its position with x and y coordinates. So you have seen that we have we have the y coordinate, and then we have x coordinate here, and here we have z coordinate, and this coin is rolling on this 2-dimensional plane, which is xy, and its configuration can be represented by, we have x, y, theta, and phi. So using these 4 parameters, we can describe its configuration. But since this coin cannot can reach anywhere on this xy plane, okay, but regarding the velocity, it cannot have a velocity along this side. It can only have a velocity along the direction of phi, but it cannot have a velocity that is orthogonal to the phi. For example, now it's moving toward the y coordinate, okay, the velocity is toward the y coordinate, but it cannot have the velocity along x coordinate without changing the angle phi. Okay, so if it has to move toward the x coordinate, then first you have to change the phi angle, you have to rotate it toward the x-axis, and then you can have a velocity along the x-axis. So here you have noticed that although this coin can reach anywhere on a rectangular two-dimensional configuration space, but its velocity can be it has some velocity constraints that limits its velocity along certain axes. So these types of constraints, they are called non-holonomic constraints, and they're also called velocity constraints. And what they does, they reduce the dimension of the feasible velocities. And another example of these kind of constraints is, we already studied about your car. For example, your car cannot move along sideways. Okay. If you want to move sideways, first you have to take a turn and then start moving sideways. But in contrast, we have studied about the omni-wheel robots that can move instantaneously also on the sideways. Okay, the next concept is about task space and workspace. Task space and workspace are related to the configuration of the end effector of the robot. They are not related to the entire configuration of the robot. So it means that when we are talking about the task space or workspace, we are only concerned about the end effector and not the So let's say we have a robot here. And here we have, these are the two links and joints. Then we have an end effector here. Or let's try to make it downward. So let's say we have a robot here. And here we have an end effector. And then we have our workspace, the task space or workspace. So whenever we talk about the task space or workspace, we are referring to this gripper or this end effector here. We are not concerned about the other configuration of the robot. We are only concerned about this end effector and its how we can describe it within this task space or workspace. The task space is the space in which the tasks can be naturally expressed. If the task of the robot is to plot with the pen on the paper, then task space will be Euclidean plane. So let's say here we want to here we have a pen, and with this pen we want to draw something on this paper here. So here we have a paper and we want to draw with this robot. We want to draw something here, and so then your task is to draw something. And this is your, let's say, your pencil here. So now you want to draw something. So we are only concerned about this task, and because the paper is a 2D planar surface, so we can describe it using x and y coordinates. You can also say that it is r power 2, this Euclidean space. If the task is to manipulate the rigid body, then task space will be the configuration space of the rigid body, representing the position and orientation of the frame attached to the robot's end effector. So if you want to manipulate a rigid body using a robot, so what you need to do is you can take the configuration or the C space of this rigid body, and you can take it as your task space, okay, and then it will be, so this was for writing, and then we have, let's say, a robot where you have to do some kind of manipulation, and you have a gripper for this purpose, and let's say a coin. So for this purpose you can say that the workspace of the configuration of this coin, which can be represented by x, y, okay, the coin should be laying on the ground, a table, let's say. The coin is laying here, and it can be represented by x, y, theta, so this will be configuration space, and we can also now take it as a task space also. Okay, task space description depends on the task and not on the robot. So as you have already seen that the configuration of space, the robot, how it's connected and how many links it has nothing to do with the task space. The task space depends upon either the configuration of your rigid body configuration, or it has something to do with the end effector of the robot. But for sure it's not dependent upon the configuration of your robot. Workspace is the specification of the configurations that the end effector of the robot can reach. So in the previous slide we have talked about the task space, which was related to the end effector of the robot and the task. Now we shall talk about the workspace. What is a workspace? So this is also, the workspace is also space where the end effector of the robot can reach. Okay, you can say it is the specification of configurations that the end effector of the robot can reach. So for example, you have a two-link robot. So its workspace will be something like this. If, let's say, at this point you have attached your end effector, so its workspace will be like this. This is the center. So this will be its workspace within all this region. So it means that the end effector of this robot can reach all this circular area. So again, notice that we are talking about the end effector. We are not concerned about the actual configuration of your robot. We are only concerned about where, at which points of your space your end effector can reach. So this will be your workspace. Workspace is dependent on the structure of the robot, and it is independent of the task. So yeah, as we have seen in the previous example of that two-link robot having a circular workspace, so it's clearly depends upon your structure, how many links you have, how many joints you have, and what is the length of those links, and how many degrees of freedom of the joints have. So this defines your workspace. Okay, and it has nothing to do with the task that you're going to perform. Task space and the workspace are different from the Cspace. So I hope that till now you have realized this thing, that task space and workspace, they are more dependent on the end effector. So task space is dependent on the end effector of the robot and the about the object or the rigid body that you're going to manipulate, or you can say the task that you're going to perform. So this will be the task space. On the other hand, workspace is more dependent on the end effector and also the configuration of the structure of your robot, how it looks like, and they're different from Cspace because configuration space, it tells about the configuration of the joints of the robot. Okay, and yeah, so a point in the task space or a workspace may be achievable by more than one configuration of the robot. So this needs another example. For example, this is our, let's say this is our task space. Not sorry, the workspace we have. So this is our workspace, and we want to achieve this point here. This we call it P1. Notice that this P1 is achievable by this configuration, and the configuration is when theta 2 and theta 1 has these specific values, then your robot end effector will reach this point P1. But this workspace point P1 can also be achieved by an alternative configuration of the robot. Okay. For example, if your robot looks like something like this, it has link 1 here and then link 2 here. So again, it will reach your workspace point P1, but this time with a different configuration space, having a different configuration. So it means that if you see your configuration space of a 2D two-dimensional and two-link robot, theta 1, theta 2, so you remember that any point can have multiple configurations. For example, a point here, this can be reached by either when theta 1 has a specific value and when theta 2 has specific value. Okay, so we are talking about point P1, not this is a configuration point. This is a Cspace point, okay, and it has nothing to do with P1. So what I'm trying to say is that the P1, the point in your workspace, it can be reached through multiple combinations of theta 1 and theta 2. So for example, the green combination of theta 1 and theta 2, it takes your end effector to point P1, and then you have also other configuration. For example, maybe this configuration here, and for this value of theta 1 and theta 2, you also get the same point in the workspace. So this is your configuration space, which tells you the specification of your joints or the configurations of your robot, and then you have a workspace represented by this blue circle. This has to do something with the end effector and how your robot is made, and it has nothing to do with your configuration space. Okay, as a point in workspace is not the full specification of the robot configuration. So we have already seen that the point in the workspace, it is more dependent on the structure of the robot and your end effector, and it is not much dependent on the configuration of your robot. Some points on the task space may not be reachable by robot. So this is absolutely true, this statement, and you can say, but all points in, so this is correction here, all points in the workspace are reachable by at least one configuration of the robot. So whenever you talk about the workspace, so it means all points whatever you have in your workspace that we talk about, for example, in the circular workspace. So pick any point in your workspace. This point can be reachable by at least one configuration, at least one value of θ1 and θ2, a combination of them. So means that we can map the configuration space for every value of the configuration space. There is a corresponding point in your workspace. Okay, so this is your workspace and this is your configuration space where you have θ1 and θ2, and you call it Cspace. Two mechanisms with different C-spaces may have the same workspace. This is absolutely, it makes sense because we already said that they are independent of each other, the workspace and the C-spaces. So it means that when two robots have a different configuration spaces, but they may have like same workspace, and the example, one of the example can be a circular workspace and this workspace is achievable by two-link robot, and the total distance is from center to the end effector is 3. Okay, and but its configuration space is two-dimensional, so we call it like θ1 and θ2. So there can be another workspace, but this is composed of 3 I think I should draw it a little bit bigger. It's clearly visible. So here what I did, I draw a 3-link joint, 3-link robot, and there its links are small, but the total distance is again 3. The total length of combined length of the links is 3. So its workspace will be this circular plane. Okay, but this time its configuration space will be different because it has 3 links. So it will have a 3-dimensional configuration space having θ1, θ2 and θ3. So you see that these two of the robots, they share different configuration spaces, but they share same types of workspace. And the robots also look different. They have a different structure. This one have, you can say it has three links, but this one have 2 link. So you can call it 3 revolute joints, 3R robot. But this one have 2 links, so 2R. So this is your Cspace, and this is your workspace. This is your workspace and this is your Cspace. So yeah, so this is the relation between your Cspace and the workspaces. The planar 2R open chain robot with the planar 3R open chain have the same workspace despite having different Cspaces. So yeah, we have described these by this example here. And the next point is two mechanisms having same Cspaces may have a different workspaces. So even if the two robots have, or the two mechanisms have same types of Cspaces, they can still have a different kinds of workspace. For example, let's see here, we have a robot 1 which has so we have a 2R robot or 2R mechanism having two revolute joints, and it looks like something like this and this, and its configuration space can be represented by θ1 and θ2. This is configuration space, and its workspace will be circular. A planar, you can say. And then we have a robot in 3 dimension. So let's make it like this. So our second robot is like this. So it's a 3D robot, and we have so this was a planar robot, okay? This was 2R planar, but this one is it has, this is 2R but spatial, meaning it's a 3D, okay? And let me do one correction. So we remove this one here. It looks like 2R. Okay, so in this case, if it's a 3D robot having two links, so this time its configuration space, because it's a 2R, it can be represented by θ1 and θ2. This is Cspace. Look, it's similar to your two-dimensional planar robot. But the difference is that this time its workspace will be a 3D sphere instead of a 2D circle. So how can we plot a sphere like this? So this will be its workspace. You have θ1 and θ2. It will be like a ball. But in this case, you have this is the workspace. Right down here, W, S. And this, for here, this was a workspace. This was a planar, a 2D circle, but here, in this case, we have a sphere, a 3D. So this proves that when we have two mechanisms, they can have same looking configuration space. Like here we have theta 1, theta 2, theta 1, theta 2. The configuration space is similar, but the workspaces are different looking. The topology may be different. Okay, so thank you very much for listening. And if you have any questions, you can always contact me by email. Have a nice day.